continue the remaining topics under salt hydrolysis. So we have dealt with three cases, case 1, case 2 and case 3, and the fourth case is salt of strong acid and strong base. So examples is sodium chloride and potassium nitrate. So sodium is the strong base and Cl is the strong acid, salt of strong. So this is the salt of strong acid and base. So already we have seen this thing. And these type of salt, that is sodium chloride and potassium nitrate, so they do not undergo hydrolysis. So these types of, they do not undergo hydrolysis. Why? Because these ions are completely converted into ions, and these ions do not interact with the water due to its strong acid and strong base. So that's why they do not react with the water, and such a solution of salt solutions are actually neutral in nature at 25 degrees centigrade or any other temperature you can say, but it will be neutral in nature. And in these cases what will happen, so neutral means we know already the concentration of H plus is always equal to the concentration of OH, and for 25 degrees centigrade the pH will be always 7. So this is the one important case of 4. So now let us summarize the whole 4 cases in a short this one table form. So I have brought in table form. So this is the hydrolysis at a glance. These are the name of salt, nature, and the degree of hydrolysis, hydrolysis constant, and pH. For strong acid, strong base, NaCl, neutral. And degree of hydrolysis, no, they are not hydrolyzed. pH, no pH. pH means neutral. This will be neutral, means any current pH, that will be neutral. Hydrolysis constant, no hydrolysis constant, because they will not hydrolyze. But in case of weak acid and strong base, that is sodium acetate, the solution will be basic because of the strong base, and the hydrolysis constant is Kw divided by Ka into C under square root of this one, and K is equal to Kw by Ka. So remember, just keep remember weak acid Ka, and pH is again basic means more than 7, so 7 plus pKa plus log C. So this will be positive. In case of strong acid and weak base, it will be acidic, so H will be instead of K, it will be Kb, and K will be Kw by Kb because of weak base, and pH will be less than 7. Less than means 7 minus pKb minus log C. So less than 7, more than 7. In case of weak acid and weak base, the solution can be acidic, basic, or neutral, anything any possible. It will be slightly acidic or slightly basic. And degree of hydrolysis is Kw by Ka into Kb, and KH is Kw divided by Ka into Kb, and pH will be always more than 7 or less than 7 depending upon the pK or pKb value. So this is the one small glance to remember the whole formula. Now we will see some other cases of hydrolysis of salts. So this is the case number E, means 5th case, that is called case number E, means 5th case. This is, so this is a hydrolysis of salt containing amphiprotic anion. Hydrolysis salt containing amphiprotic anion when cation, so cation is not going hydrolysis, only amphiprotic anion is undergoing hydrolysis. So in some salts where anion is an amphiprotic, so amphiprotic we know very well, it is a proton donor or proton acceptor, so both is possible. So like we have example sodium hydrogen sulfide, so this is amphiprotic anion, or sodium bicarbonate is also amphiprotic anion. So this can also lose hydrogen, this can also gain hydrogen. So when such a salt, let us take HX. HX means this can be anything, CO3, anything sulfide. It dissolves in water. So when this is dissolved in water, what will happen? The amphiprotic anions of following equilibria, and here only anion will undergo hydrolysis. So anion will undergo hydrolysis means just like that. See here. So this is the sodium hydroxide. It is undergoing so Na plus and HS minus one aqueous solutions. So what will happen? This sodium will not react because we know this is a strong base. This will only react. So if HS as a acid, acid means they are proton donor. So this anion react with the water. So as a acid, what will we have as a base? So this acid base equilibrium, if we undergo ionization, H3O plus and sulfide minus. So we can write here for Ka2 because second hydrogen is there. So Ka2 will be concentration of this into this by this one. So again, if this same anion will undergo it acting as a base. Base means proton acceptors. It will react with the water. So reacting water means it will undergo hydrolysis. So on reacting in the water, it will form H2S and OH minus. So here it is as a hydrolysis. So here we can write for KH, H2S, OH minus, and HS plus. So this is our KH as a hydrolysis reacting as a base, and as a acid reacting with the water. So this is the acid and this is reacting as a base. Now here one more thing is that if it is undergoing acid hydrolysis, then what will happen? Suppose the concentration of this is more than this one, so its solution become St. If the concentration of this is more than this, then more than means predominant over the solution than this one. And if we undergoing hydrolysis, means that is the base hydrolysis, the solution will be basic. If you are undergoing concentration of H plus is more than the base hydrolysis, then the solution will be acidic. So these two are the concentration of H plus and OH minus. So it only determines the nature of the solutions. Also, for first dissociation of acid, that is H2S. So H2S is undergoing ionization, H plus and H minus. So Ka1 for this reaction is this much. This is the equation number 3. So now from 2 and 3. So from 2 and 3 multiply KH into Ka1. So you will get this equation. This is the KH, this is the K1. So you will get finally KH plus and OH, which is nothing but the KW. So we can write KH into K1 equal to KW or Ka1 equal to KW by KH. So from here we are getting KW by KH. Now we will take again KH by, take the ratio of KH by Ka2. So on taking you will get this is the KH, this is the Ka2. So Ka2 is already we have seen. So this is the Ka2. So on Ka2 we will get this one equation. Okay, so K is this second equation. So we'll see here. So here I have written if the acid concentration is more than the OH, so it will be acidic. If OH will be more than acid, so this is basic. If both are neutral, so already we have discussed these things. So here we can see that HS minus and sulfide minus. So this HS is still cancelled. Now we left 1, 2, 3, 4. So out of this OH and H plus, so here we can see, but HS means has a low degree of dissociation, so low degree of hydrolysis. So HS both having a degree of dissociation very low and their degree of hydrolysis also very low. So we can assume that concentration of H2S is almost equal to S2 minus. So consider this will be almost equal to this one. So this is cancelled, and due to the low degree of dissociation hydrolysis of HS minus, so this is almost equal to each other in equation 1 and 2. So that we have seen it. Equation 1 and 2, let me show you once again. So like this equation is there. So this will be almost equal to this one. So if the degree of dissociation of this one is degree of dissociation and hydrolysis is very less, then this will be equal to almost each other. So on that basis what will happen, we can take H2S is equal to S2 minus. So again this KH by K2 will be equal to this by this, that is the OH minus H plus. So now we can write here OH minus is equal to H plus into KH by Ka2 and KW by KH. So we can write here, this we already know that KW by KH that is equal to, this is nothing but the KW by KH, because KW equal to H plus and OH minus. So H plus is KH by KW, so we can multiply, on multiply this becomes H square KH by K2. So again this H by H square equal to KW by K2 by H. So this is if you solve it, if you take the square root, so this is nothing but the Ka1. This is whole is equal to Ka1. This we have already solved in the previous examples. So this is the Ka1. So we here we write here from equation we have already seen. Let me show you. Already we discussed this one. Ka1 equal to Kw by Kh. So from here K1. So K1 Kw by Kh equal to K1. So this is K2. So H plus equal to a square root of K1 into K2. So H plus is minus log of H plus, so minus log of K1 plus K2 half, or P is equal to half of log K1 plus log K2, or pH of sodium hydrogen sulfide will be equal to half of pK1 for H2SN plus pK2 plus HSN negative. So in the above calculation we have seen that only anion is undergoing hydrolysis. Okay, and if the cation and amphiprotic anion both are hydrolyzed, so now if these and both are hydrolyzed, then H plus be calculated as follows. For example, ammonium hydroxide, ammonium bicarbonate. So let us take in the next case, that is the case number F. This is next is case number 6. So fifth we have seen it. So hydrolysis salt having amphiprotic anion in which cation undergo hydrolysis. Even cation plus anion both are undergoing hydrolysis. So we can write here cation and anion. So anion already given here, so both undergo hydrolysis. So we can see example of ammonium ammonium bicarbonate. So ammonium carbonate in water, it will dissociate into ammonium ion and bicarbonate ion, and both will react with water. So this is also reacting with water, this is also reacting with water. So let us see one by one. So when ammonium ion, this is reacting with the water, so it will form ammonium hydroxide plus H plus. So this is called cationic hydrolysis. So cationyl K is equal to Kw by Kv. Now for this one, K1 will equal to, suppose this is Ka1 first hydrolysis, so Kw by Kb will equal to, this is formula. And now bicarbonate also react with water, so it will form here this equation, this is called anionic hydrolysis. So K2 will be Kw by K1. So this is the equation, and this is the K1 is nothing but the this is the first dissociation constant of H2CO3. So this is the Ka1. So this is the nothing but the first dissociation constant of the H2CO3. So this we have taken. So what is the dissociation constant? Let us see that. So again this K1 for this reaction, this is the HCO3 minus, it is undergoing dissociation like H plus and CO3 carbonate minus. So for this K2 will be H plus and CO3 whole concentration of carbonate plus H plus divided by concentration of HCO3 by law of mass action. This is the this is the third case. So from third case K1 is this one, and fourth case K2 will be this one. Now here we have to keep in mind one more thing. We are applying mass balance as the initial concentration. This is the concept of mass balance in the initial concentration. What is the mass balance? Mass balance means the concentration, initial concentration of ammonium is equal to the initial concentration of bicarbonate ion. So let me show you this one. So if you remember, so ammonium bicarbonate by dissociation into ammonium ion and carbonate ion. So initially concentration of both are equal to each other. Okay, so when this is undergoing dissociation of this and this, and bicarbonate is going under dissociation this and this. So this is the undissociated, this is the undissociated, this is undissociated, this undissociated is equal to concentration of dissociated plus dissociated, dissociated plus dissociated. So we will take this plus this equal to this plus this. So see here we have taken here. So ammonia is dissociated into undissociated ammonium plus ammonium hydroxide. So both will take at equilibrium. So we will take here this plus this plus this is equal to concentration of this plus whole this. So here ammonium is, that is from here we will getting two concentration, this one, and for bicarbonate we are getting this one and two from this one together. So if you remember, so this is the undissociated at equilibrium is equal to dissociated at equilibrium. We are taking only mass balance, and carbonate is giving SCO3 minus. So this is the undissociated bicarbonate, this is the dissociated, and this is the, instead of H plus we will take the CO3 minus H plus, or you can say OH it is H plus. So OH minus equal to carbonate, equilibrium concentration of the carbonate. So it will be equal to here at equilibrium. So now using the constant equilibrium, that is 1, 2 and 4, 1, 3 and 4. So 1, 3 and 4 means, see here. So this is the, let me show you. This is the constant of 1. We have seen it. This is the constant of, so this is the constant of 2. This one, constant of 3, and one more is the constant of K2, this one. So we will use this relationship in this one. So here NH4 plus is equal to concentration of ammonium hydroxide. So you can see the ammonium hydroxide. So ammonium hydroxide is this one. NH4 will equal to Kb, W by Kb into ammonium divided by H plus. So you can see here. And similarly, this is the ammonium bicarbonate. Right like this, and this H2CO3 will be written as a, so Kw by K1 you can see here. So H2CO3, so H2CO3 will be Kw by K1, this will be this side, this will be down. So we can see here, and similarly K2 will be HCO3 by H plus. So already we have seen it. So this is the K2. So K2 will be concentration of CO3 will be this into this divided by H plus. So this is the concentration of this one. So this will be H plus, not H plus. So this is equal to this one. So now take the ammonia out. So on taking ammonia out, so 1 plus Kw by Kb into 1 by H plus, and this will be SCO3 if you are taking outside. So this will be 1, this will be this by this by this. Now for higher concentration, what will happen? The concentration of ammonia will be equal to concentration of bicarbonate. So this will be equal to each other. So let's cancel it. If you take the big concentration or large amount of concentration, then this is also cancelled. So this then minus this one. So this minus K2 minus H plus. So whole divided by K2 equal to H plus by K1. So we can write it KW by KB, and H is taking this side, so it becomes a square. So H plus square into K1. So H plus equal to square root of K1 by KW by KB minus Ka2. And multiplying by the log on both sides. So minus log of H plus minus log of half. This will convert to half log Ka11 KW by KB minus Ka2. So this is nothing but the pH. pH equal to, this is pK1 minus half of log KW by KB into K2. And here we can see all are constant value. So in this case pH is independent of initial concentration. So in this way we can find the pH of this amphiprotic anion plus cation, which is independent of concentration.